So, what changed? So there's an important reference. We have to be real careful when we go through and read these to understand what's going on. Did we gain in OH? We lost in OH. What else happened? The right side? Didn't you say the right? Or you want left? Okay. Well. So in that case, yes, you gained in OH. Okay. We lost an H. Is that it? Yeah. Okay. So, is there a chemical reaction that allows that to happen? What kind of chemical reaction would involve the loss of one bond and the gain of another? Cool, substitution. That should be pretty suspicious because that would suggest one step, in which case it wouldn't really be a synthesis. So let's push on what we need for a substitution. What do you need? That means the basic components of what you need to do a substitution reaction. What are the things that need to be present?
Leaving group.
We need a leaving group and a nucleophile. Okay. If we go through and look at this, the leaving group left, so that would be our negative, our loss, and the nucleophile would be positive. Okay. Or not positive, it would be our gain. Okay. So if we go back to our changes, positive OH. Could the oxygen be a decent nucleophile? Okay. So with the pause, maybe that means we need to go back and actually say, what the hell is a nucleophile? What is a nucleophile?
Electron donor.
Cool, it's an electron donor. So what would we expect to find on an atom that acted as a nucleophile? Lone pairs, okay, a source of electrons. So back to the question at hand, because this is the plus, the gain, we'd be talking about the OH being our potential nucleophile. Could OH act as a nucleophile? Yeah? Why? Okay. Minimally, the oxygen has two lone pairs. Okay. That would be a source of electrons. It is technically missing a group of electrons, okay, out here. And what could be in that group of electrons? I argue there's two options. What do you want it to act as? We want it to act as a nucleophile. A nucleophile would be an electron donor. An electron donor would be something with lone pairs. It would be a source of electrons. What would be a good thing to put in that box? Let's put a pair of electrons in it. That would be lovely. Okay, we put a pair of electrons in it, and that takes us next tier or next level, because then what happens to our oxygen? It would be negatively charged. Would a negatively charged oxygen work well as a good source of electrons? Ooh, okay, that fits the pattern. Or what else could be there? A bond. But do I want that bond to appear in my product? No. So it could be a bond there, but that bond would need to be something easily broken. Like hydrogen. Okay. So I could look at the nucleophile as potentially being hydroxide with the negative or water. I get two potential nucleophiles here just by breaking down what changed, what reaction that means, and then understanding what the components are part of that reaction. That's why those definitions got pushed so hard in OChem 1. so that you can find and follow those pieces instead of just trying to throw reagents at it. You need to be able to focus your thought process. Okay? What's the other component that we need for our substitution? And if we're wondering, that's okay, but this is why we take notes. And in our notes, it said substitution, we needed two things. We needed a leaving group and a nucleophile. We just addressed the nucleophile, which means, what do we need to address? The leaving group. Okay? That would be the negative thing, the loss of the leaving group in our process. If we looked at the thing that was lost, what was the thing that was lost? Hydrogen. Okay? We just said hydrogen was something that was okay to get rid of down below, right? But down below, what is it getting rid of as? A positive. It would be H+, because the oxygen would take the electrons. If we look at the leaving group, it's acting as a leaving group. And what's the meaning of a leaving group? What is it doing with the electrons? It takes them with it. It leaves with electrons. Which means if we're talking about H being our leaving group, we're looking at H-. Is H- a good leaving group? No, why not? Why is it unstable?
Because hydrogen's incredibly small.
Charge is negative. Negative things, generally speaking, we would say are bad leaving groups. Okay, but there are exceptions to that, which is why we could then move to size. Hydrogen is the smallest element on the periodic table. Okay, it cannot stabilize that negative charge. Okay, that would suggest that's a trash leaving group. What does this mean for us? Can we get away with just the substitution? No, because the hydrogen that we need to remove is not a good leaving group. Okay? So it doesn't fit with our patterns. Something else has to happen here. So what we might go back and do is say, did I miss something about the chemistry of either of those two things, the reactant or the product? Okay? And hopefully when we go through and look at it, we'd be like, well, I didn't really miss anything. Okay? I gained an OH and I lost the H. Both of those things are fine. Okay? Nothing else changed. Well, now we can zero in a little closer on our reactant because that's our problem right now. And we look at the reactant, what chemistry is available to us? Lovely answer. Nothing. It's an alkane. Carbon, carbon to carbon, carbon to hydrogen. Those are nonpolar covalent bonds. There's very little, if any, chemistry associated with that functional group. Okay? This is why we pushed recognizing bonds types in OChem 1. Because we can now look at this structure and be like, well, crap, this doesn't react. So now what do we do? There's two answers. One, you say F it and you skip it and you move on. That's fine. Okay, hope for something better in the other one. We look at the other question. The other question at least has polar covalent bonds in both materials. So that could be an easier question to address. The other thing is actually addressing what, again, is talked about within the chemistry. Alkanes can absolutely react, but you have to do something a bit crazy. Some might say a bit radical. Okay? And if that immediately goes, oh, well then screw it again. Move on to the other one and hope for the best. Okay? Radical chemistry will show up. It will show up again and again and again, particularly in synthesis. Because when we talk about synthesizing different chemicals, okay, nearly everything that we manipulate in our chemical world, all of the chemicals we work with come from one source. Where's that one source? This is neat. Petroleum. Okay? If you think of all the things that chemistry has done for us, about 90% of it comes from petroleum. The stuff that we pump out of the ground and then we burn and turn into something we can't use. if there was ever a reason to move away from fossil fuel consumption, that's a big one. Okay? Our entire chemical foundation is based off of those hydrocarbons. Okay? And petroleum is just hydrocarbons. Under high pressure and heat inside the earth, okay, we can remove oxygen from all of those bonds and we replace them with hydrogens and we saturate our carbon structures. Okay? Those are now fully reduced compounds. If we're going to do anything to them to change their functionality, we had better hope that we can change it. That's the point of radical chemistry. So radical chemistry comes in with those hydrocarbons and just starts doing wicked stuff. As it does wicked different things, we can either try to control it or we just say, F it, let it run, and then isolate whatever products come out of it and then use those as now starting points to do everything else. Okay? So the radical chemistry that you've been told that you need to work with, okay, would hopefully do what? Say again? Okay, create an H2. What class is this? Organic chemistry. And in organic chemistry, what do we study? What's an organic molecule? Something with carbon. So does it create H2? More or less, yes. But do I care? No, because that's not organic chemistry. What I care is what happened to the organic molecule. Okay. So what's going to happen is somehow we're going to make a radical in here. Okay? That's looking at an intermediate along the path. Okay? That's okay. That's valid. That's looking at mechanistic detail. You're not being asked for mechanistic detail. You're being asked for reaction chemistries. Okay? So if we, again, big picture and say, what do we want the radical to do? The radical reaction needs to do something for us. What is that something? That's looking at the mechanistic detail. I don't care about the mechanistic detail. Big picture. What should it do for us?
Should it form an alkene?
Why an alkene? And it doesn't even have to be an alkene. Why do you want an alkene?
Because you can react it and get the other.
There's some chemistry associated with the alkene functional group. So if the radicals made alkenes, we now have addition chemistry we could run with the alkenes. Okay? What else could they possibly do? What was wrong with our starting material? It had no reactivity because it had no functional group. So what do we want the radical chemistry to do? Make a functional group. Okay? That's it. I just want a functional group on there. Okay? Once I have a functional group, I can do something. Could that be an alkene theoretically? Yes. Could it be something else? Yes. What is it? The is it question or the is it answer now comes from, did you actually watch the content and memorize the content on radicals? Because you were told explicitly you need to memorize the content on radicals. You shouldn't deal with much else. Just memorize these reagents because those reagents, the details, initiation, propagation, all of that, are usually not all that useful, and we just need the reagents. Did you? No, that's perfectly acceptable, okay? I get it. Decide there's a line, I'm not crossing that line, Mike, I'm going to go back and do the other stuff. That's absolutely fair, I get it, okay? But that's how you need to answer this question. You need to know what's going to come out of this radical reaction. And what's going to come out, based off of what you were told, is you're going to halogenate it. You're going to put a bromine on there. How do you do that? Oops. No, I did that right. Did I do that right? I did that right. Br2 in light. Br2 runs a radical reaction, or Br2 can act as an electrophile, and that can do all sorts of crazy things with alkenes. Okay. How do we know it's doing radical? Because we're adding light. What happens? Light splits the bromine into the bromine radical. The bromine radical reacts with a hydrogen on our alkane to form the most stable carbon radical, being the tertiary radical. That tertiary radical that can react with another bromine to put the bromine on, and ta-da, we now have a functional group. That functional group gives us a handle that we can now grab a hold of, and we can now potentially do some chemistry. So if we go back to what happened above, the leaving group, to do the substitution, we wanted OH as a nucleophile. Phenomenal. We had no leaving group. Right? So with no leaving group, we had to rethink our process. That rethink took us to radical chemistry. Does that mean all of our thought process on substitution is invalid? No, because ultimately what needs to happen? I need the OH on the structure, and it's going to have to substitute for something. Okay? So oxygen as a nucleophile is still great. Do I now have a leaving group? Oh, look at that. The work that I put out where I thought through all of those pieces now sets me up with a position I can say, ta-da, I've got something. I now have a leaving group, which means with that leaving group, I could now somehow bring in my oxygen nucleophile, and we'll address that in a second. Okay? And we would hope that the end result of that would then get us a product. What kind of substitution are we doing here? Or rather, what mechanism? So now we have an idea of reagents. We know what our product is. We know what our reactant is. We need to know how this works to ensure that the reagent we're using matches the how. Okay? So we go back to the substitution. And substitution, how does substitution happen? Cool, we could use stepwise or simultaneous. There's way too many letters in those for me to write them out. So instead we'll use, thank you, SN1 and SN2. Okay? We don't technically know what the nucleophile is. Okay? We have two options. It could be negative hydroxide or it could be water. It could be either one. We don't know which one. Okay? So you say, oh, it's going to be SN2, so it needs to be strong nucleophile. Well, is it SN2? Should it be a strong nucleophile? How do I decide what information is already locked in that I cannot change? Sort of there. When we think through our substitution, there's certain components that we have to address when we think about substitution. We have nucleophiles. We have leaving groups. That's awesome. What are the other two components that we need to worry about with substitutions? That's the complication. We'll come back to that one. Backside attack and carbocation are our large picture. Oh, it's because I butt tapped the wire. Are the large picture ideas. Okay. What are the components of our substitution? Leaving group, nucleophile. There's two more components. Sort of. Substrate is the big word. This connection is so stupidly finicky. I'm pretty sure they brought in the same dumb cord that they shouldn't have used last time. Pretty sure this is an Amazon issue. Sorry we woke you up.
What? Oh,
Come in yawning.
it's because I'm tired. I just got off work.
Come on.
Shouldn't class started like 10 minutes ago?
Yeah, there are 4 components to a substitution reaction. We are already in it. It's recording.
Oh,
The class has so far addressed 2 of those components, nucleophiles and leaving groups. What are the other 2 components? Technically, Abby, yes, you're right.
Thank you.
Sorry, I left you a little dramatic pause there. What are the other 2 components?
a base?
No. solvent is a good component, okay, or a component. We typically ignore solvent effects. This connection is shut. I really don't want to whiteboard this because that's going to lose our recording.
Oh,
Stupid computer. So solvents are perfectly valid and acceptable as an explanation, except they are rarely, if ever, referenced. And when we're talking about the overall chemistry that we're running through here, let's see, dot cam. Oh, it's not even acknowledging the dot cam. It's just decided to entirely, let's just go with wet the bed.
did you already restart your computer?
It's not my computer. I'm gonna be real pissed. I'm gonna delete it all. Because I would bet you, yeah, my computer acknowledges that it's plugged in.
Oh, dang. What port did you touch?
The HDMI cable. And they, for whatever reason, have purchased, okay, we at least got the dot cam cable functioning, and it's less likely for me to butt tap that one, so. If I get lucky, don't hint me, don't show again. Resume. Oh, come on.
Could we go steal some from,
It says it's connected.
is anybody in lab right now?
Oh,
Does you have
are
an
you?
HDMI cable in there? Swap it out.
The problem is what is that HDMI cable connected to? This locked box. It says it's connected. Why aren't you projecting? It doesn't like me. Nobody likes me. That's fair.
Oh.
Yeah, but that's the PC.
Oh, well.
Maybe. It doesn't even want to show the PC? Okay, so maybe I didn't butt tap it. Maybe it just
Oh.
Maybe you just died. Oh.
yeah, because the PC has projection here. Should be able to see it. Okay, well, I'm just going to record from here on out. How am I going to play this? So we'll just do it like this. I'll record and attempt to take notes in both places. The recording should at least pick up what's on my screen. It just won't project. And then I'll try and write on the boards.
Do YouTube live.
Well, I can YouTube live on my computer. That still doesn't go to the screens.
Well, if we all have our own computers.
Of course, yeah, we go old school and there's no freaking pens. You gotta be kidding. So, our substitution. Substitution patterns, we said we had our leaving group, we had our nucleophile, we had solvent, and we had substrate. The leaving group we've already sort of addressed. We fixed, we turned it into a bromine. The nucleophile is what we're ultimately trying to figure out. We're trying to figure out what should be in that box with the oxygen. We said there were two possible options, either the lone pair or hydrogen. Right? And if it was the lone pair, we're looking at a negative, and then this would push us through to the substitution result. Okay? Since we don't know what's going on with the nucleophile, we can't use that to evaluate which mechanism we're running under, which then leaves us looking at the solvent or the substrate. The solvent would be something we would put in the middle anyway, so that would be our choice. Again, not useful to reference. So the only thing that we have that we can actually reference would be the substrate.
Oh, shit.
What kind of substrate do we have?
Bulky.
We can run with bulky. I think we can work with that. I don't like that wording, but that's okay. I don't have to like it. Okay, when we talked about substitution, we said there were two mechanisms, so also summarized. We had the SN1 and the SN2. The SN1,
Carbocation.
I don't think I wrote this up on the notes, but this was on the screen at least. Carbocation, SN2 was backside attack. So if you're going to say bulky, which mechanism does that support?
Carbocation.
Okay, carbocation. So where I would have gone is not bulky, but I would have called that tertiary. Okay, where the bromine's connected, it's connected to 3 other carbons. That is still bulky. Okay, and the reason why I would put tertiary is that if we talk about tertiary, does that bring up any bells for stability as far as carbocations?
Yeah.
Does bulky bring up any bells for carbocations?
No.
No. What it should bring up is backside attack is a bad idea. Okay, so in that context, bulky works because you're saying backside is bad.
I mean, doesn't
So-
bulky kind of work because it's all about the electrons around?
It does. So, and it's just, where's the word game association within your brain? If the word game lines up, great, you're fine. If it doesn't, we've got a problem. Right? So what does that mean? Tertiary substrate, that means carbocation. What is that going to tell us about the nucleophile or the solvent? We would need a weak nucleophile. Is the -1 a good choice?
No.
No. Hydroxide would be a bad choice because that would be a strong nucleophile. That doesn't make sense as a reagent. Instead, what we'd want to do is drop in the hydrogen. So what we'd be looking at, for the sake of the people in the recording at home, we'd be looking at water as that second reagent. Could we have put hydroxide? Okay. I would see it and at least acknowledge that you recognize what needed to change. Okay. Does hydroxide work?
No.
Why not?
Because it can't do what's required for an SN2 reaction, which is a backside attack.
There becomes the issue. If it's hydroxide, it's sterically small so it could theoretically try and do a backside attack, but the substrate's large, so it can't. Okay? But it's negatively charged, and negatively charged is a strong nucleophile and a strong base. If we did hydroxide, we're not going to get the substitution that we would want. We'd actually get the competing mechanism of E2 when we get the elimination. Not what we wanted in this case because we wanted the substitution, which is why we needed water there. Kind of, sort of? Does that answer it?
Yeah.
A little bit distractedly and all over the place, but at least we're there. All right? Questions about any of that?
There was something you said in the videos about.
Dangerous way to start a question, but okay.
Oh yeah, something about hydride being small, but then it's still sterically large. I was very confused by your explanation.
So that is a question from the videos.
Yeah.
What you were talking about there is an interesting dilemma. If we go through and look at some bases, we'll take a look at 2 bases. Okay, we've got hydroxide, okay, as a classic base. Okay, that would be a classic strong base. And as we just addressed with hydroxide, what else could it do? It could act as a nucleophile. Why could it act as a nucleophile?
As lone pairs.
It's not just because it has electrons. Because if I switch this up to this thing that has lone pairs with the electrons and throw that on, that ain't a nucleophile anymore. Why can the hydroxide act as a nucleophile? It's a good nucleophile because it's small. That small size allows hydroxide to act as both a base and a nucleophile. So why does this become important? Because typically when we talk about hydroxide, we look at it as sodium hydroxide. And in the videos, what we're starting to look at is other bases that are out there. Okay? And the one in particular that you're talking about is sodium hydride. Okay? And if we were to go through and look at sodium hydride as a base, what would we say about its chemistry?
real strong.
Okay. Why do you think it's stronger than our sodium hydroxide?
My best guess is that hydrogen really, really, really doesn't like being negative like that.
Why?
It's not very electronegative. Is that a good explanation?
Partly. I'd say you're half of the way there. How do we decide what that chemistry is? How would we figure out whether it was good or bad at something?
You test it out.
Or,
Draw it out.
sorry, I'm focusing on trying to write some of the notes down for the lecture recording. Well, if we were going to look at its chemistry, and in particular if we were going to compare it to hydroxide, H minus OH minus, we might go through and say, well, is there a charge difference between them? No. Then what we look at? We might look at the size. And if we look at the size, is there a difference between oxygen and hydrogen? Yeah, they're in different rows. Hydrogen is the smallest possible element we've got. Okay, so what does that mean about its ability to stabilize those extra electrons? It can't. Okay? And if we weren't satisfied with the size, then what might we want to then move to? Our electronegativity. So where you jumped to was electronegativity. I would like that you start through this pattern. Why? This pattern organizes a logical flow of thought and reasoning that allows you to correctly navigate how you would move through determining strengths of reactivities, be it acids, bases, nucleophiles, or electrophiles. And if instead of moving through this, you're just, I think it's resonance. Maybe you're right, but the only reason you'd be right is because you knew the answer, in which case you didn't need me anyway. So the process behind this is that theoretically you don't know any of these answers. What is your flow to how you achieve those answers? What are you thinking through to move that? The whole point of the charge, size, electronegativity, resonance, induction, and oh my God, is to worry about what those kind of flows are to ensure that you don't make a mistake. The most common mistake that I'll point out is that guarantee everybody in this class, including me, is going to jump to induction at one point or another to explain the difference in reactivity between two molecules. And you'll get it wrong. And you'll be like, well, why not? Induction explains it. You're right, it does. But you didn't address that resonance was the issue, and resonance trumps induction. Which is why you have to navigate through a system that ensures that you don't miss those other pieces. Okay? Does it have to be written down? No, it does not. Right? But it should be moving through your head, and when we talk through it in class, if you aren't explicitly making those statements, I'm going to throw this back in your face. Does that make sense? Okay. And just because sometimes we can get some confusion with this, we added the whole AMO thing. Because these are atom effects, these are molecule effects, and then who the hell knows, it's all over the place. Okay. This category can be atom effects, it can be molecule effects, it can be anything, but usually you're looking at very refined differences, and that's not particularly useful. Okay. So if we go back now to the question at hand, hydride versus hydroxide, we would say hydride is wicked unstable, and because it is wicked unstable, it would be phenomenal as a base. And because it is wicked small, it would be phenomenal as a nucleophile. And yet what happens is that when we go through to try and use sodium hydride as a nucleophile, it doesn't work. And it exclusively acts as a base. And the question kind of comes, well, why? Why can it not act as a nucleophile? Well, what's that defining feature between nucleophiles and bases?
I thought it was size.
Yeah, size. Size is that big defining feature. The bigger it is, the more likely it acts as a base, and the less likely it acts as a nucleophile. And when we look at hydride, we'd be like, well, hell, it doesn't get any smaller. Why can't that act as a nucleophile? What this hinges back to is how incredibly unstable hydride is. It is so unstable that it seeks out positives and it refuses to let go of them until another positive comes along. Which means if I take sodium hydride and I try to add it to an organic solution, what happens? It doesn't mix. So I never get hydride solvated into the solution, or I get a very tiny amount of it. And if it never makes it into solution, well, what you're looking at now is a multi-phase system, a liquid and a solid. I'm not looking at sodium hydride as a small molecule. I'm looking at it as a large frickin' solid. There's the steric hindrance. Okay? And that becomes the issue with the sodium hydride. Is that something you would ever see on paper? No. That would be something you'd go into lab, you try to dissolve it, and it doesn't dissolve. Well, it doesn't dissolve because it is so incredibly unstable. So what happens is your solution floats over the surface, encounters it, and it's going to encounter it in the case where it's the most accessible. That's going to be hydrogens on the surface of your molecule. That's why it's acting as a base, not as a nucleophile. Does that make sense?
Yes.
Okay. Just because we're on this topic and we can always make this fun and more dangerous, does that mean hydride can never be a nucleophile?
I'm assuming, based on the way you asked that, no.
No, hydride can be a nucleophile. It just can't be a nucleophile in this particular scenario.
Say if it was a non-organic solution, then it could possibly?
Well, a non-organic means you're moving up to like water. And what's the problem with water? It's pretty stupid acidic in comparison to most organic solvents. Okay, so water, when you mix sodium hydride with water, that's called explosion. Okay, so we don't worry about it acting as a nucleophile there, like it's acting as a base and it forms hydrogen gas and enough heat to instantly ignite it, and that's unpleasant. Okay, so if we want hydride to act as a nucleophile, what we have to do is ensure that whatever it's connected to can stabilize and reduce that negative charge enough that it's now stable and can dissolve into solution, but not so much that it's not negative. So we would need a different element to counterbalance it. Okay? What if I put a carbon next to it? Would that hydrogen be negative? Why not? What would it be?
Well, they're both partially positive.
What do you mean by put it next to it? Like connected to
Bonded.
it?
I'm totally drawing something on my iPad. That was stupid, Mike. Okay. We've got our hydrogen. We want it to be negative. We have to bond it to something where it still maintains that negative characteristic.
Like a metal.
Okay. And if we throw a metal on it, the problem is we have an ionic bond. An ionic bond means the hydrogen is negative. That kind of shafts us. If we put a carbon on it, what charge is our hydrogen? Positive. I wanted it to be negative. Okay? And even then, how positive is it? And. It's so similar that we call that a non-polar covalent bond. It's effectively a zero. Okay, well, let's try an oxygen.
Same problem.
That's even worse. Like, that's fully positive. Okay, so we need to put something here that's not a metal and not carbon, nitrogen, oxygen, or our halogens. Sodium borohydride sound familiar? That should sound familiar because that's the follow-up to our mercury addition. We're talking about our oxymercuration reactions. How do we get rid of the mercury? Sodium borohydride, where hydride, it's in the name, replaces the mercury on our carbon structure. We do have hydride nucleophiles, but we have to change the chemistry by what they're connected to reduce some of that negative impact so that it's stable enough to be able to dissolve into solution. Okay. Kind of make sense? Cool. And then for the sake of the recording, I'll draw that out while you tell me if you have another question. Cool. I like the right part of C. I think that's a good question for the boards. God damn it. He knows also, but we just reviewed it for everybody else. Where's the first place we start? What change? Identify those changes. Come up with whatever notation you want. For the sake of what I had done for it, it was plus, I'm gaining, minus, I'm losing, and writing those changes out. Once I have the changes, I can then kind of negotiate what's going on with everything else. And then talking only for the people at home, what I will go through and do, because all the kids are drawing stuff up on the screens, is I will draw out the reaction and start to put down some of those changes so you can kind of see what's happening with the rest of the classroom. You might hear me yell as I'm yelling at the rest of the classroom to do something else. But here's our synthesis that we're being tasked with, and to the directions of what we talked through. I want to gain a bromine. I want to lose an OH. I might go through and call this a substitution, but I have a problem. Problem is chemistry is at a different position. If I had been a little bit more careful with my changes, hopefully what I would have noticed is that I have also gained a hydrogen, ta-da, and I have also lost a hydrogen. So we've got a few more changes going on behind this. It isn't just going to be a straightforward substitution. I'm going to have to run a couple cycles behind this. Okay. If I'm going to then switch this around, what I might go through and do is say that I want to take my losses, okay, those two lost together would be the loss of 2 sigma, which might give me a gain of a pi bond if I could pull that off. So if we were walking through that, what I'm hoping I would be able to pull off would be something like that. And since I don't want to give anything away, I'm going to go ahead and pause there, but you can go ahead and think about that process and think if that is a valid reaction or not. So hopefully you're able to discover that if we were trying to get rid of those 2 sigma bonds, the OH and our H, that's not going to give us the least substituted pi bond. It would give us our most substituted pi bond. And we're going to get a pi bond forming inside the ring. Right? The other issue that we might note is that our leaving group is not a good leaving group, so we would need to somehow change that leaving group. The option typically thought about is to add H plus to turn it into water as a leaving group. The problem with water as a leaving group is that to get the Hoffman elimination or the external pi bond, you need a bulky base. So what it looks like the class has now come up with is that instead of converting the OH into H2O, is that if we instead convert it into a bromine, the bromine is now a better leaving group, and it negates that issue of the acidic hydrogen. What the monkeys? Okay, at least it came back. Negated the issue of the acidic hydrogen, which then means we can throw a big bulky base at this. The big bulky base will go through and get us the elimination we want. Our good bulky base T-butoxide works out great and sets us up with that scenario. This now sets us up to be able to navigate the last little piece. And the pieces that we have not addressed would be the addition of Br and the addition of H. And again, I'll walk away and see what the rest of the class is coming up with, and we'll come back here in a second and see if they've come up with a good answer. And I'll see if you've come up with a good answer. So if we go through and look at these pieces, everybody else in the class got up to this point, and that adding H and Br would in fact give us exactly what we want in the wrong spot. That would put the bromine at the most substituted position. We don't want the bromine there, we want the hydrogen there. So we want our atoms going the opposite location of where we would expect them or predict them to go. Someone might have said in the past that if we want atoms to do something crazy and go the opposite direction of where we want them to go, we might want to do something a bit
I mean, the BR2
radical.
is still going to work, right? Because if you put the BR2, you were close to
No, I think we don't think it doesn't work
a
that way.
negative right there or a positive right there.
And then the last little hint for the recording, which will also work for the class, we can just go with roar. So hopefully what you all are doing is now looking at your boards. In fact, we can go ahead and switch. Take a look at the boards. Make sure you see the work that's been put in behind those. Try and understand what's happening. The logic and the thought process behind it becomes the important aspect. Okay, so again, I'll throw it out there again. Switch. Look at the board, then do a last switch. Look at the original board that you were at. Then you can go ahead and sit down. I did take notes, right? Those notes look okay? Yeah? Okay. So it is in the recording. It's ending about 46. I might have started this about 40. So if you wanted to walk through with my kind of quiet whispers and the reaction stuff that I was notating down while you guys were running your reactions, fast forward to about 40 minutes and then you can watch about 5 minutes of stuff. Just watch out for that roar hitting you about 45. Sorry. Tough for the people watching the video at home. So if our HBr is the reactive thing, how is it reactive? Okay, so we could reference it as donating protons. I fully accept that, but one shift I want to do is pull us back to the directions, and the directions say provide the mechanism. And when we talk about provide the mechanism, what are we talking about doing? Moving electrons. So if you're telling me donates the proton, you're not talking about moving electrons. You're not wrong, but you're also not framing it in a way that allows you to solve the question. Does that make sense?
We're saying the electrons go to the leftmost part of the pipeline, from our perspective. Does that make any sense?
Not at all what we were talking about. There's no pipeline between H and Br. You were the one that said we look at HBr. Why the frig are you going back on that one? Okay, HBr was the most reactive thing. By donating protons, what we're talking about is the electrons in that bond go where?
Towards the bromide.
Towards the bromide. Okay? This is where it actually split, and you had multiple options here. You could show what picks up the hydrogen, or you could have shown this splitting into H plus and Br minus. In my opinion, it's six of one and half dozen of the other? Okay, I don't really care. There are some people that really, really, really care. Okay? HBr is a strong acid. It should dissociate. What we're looking at is its reactivity. Okay? The issue with that is it dissociates. It's not going to dissociate into H plus and Br minus. It's going to dissociate into whatever the solvent was that was basic enough to pick up the hydrogen before it reacted with our alkene. Okay? Since we didn't specify that, I don't care. Okay? But that arrow is important. Okay? And we could show that as its own individual step, or we could split it and bring in the alkene. Okay? If we bring in the alkene, now what becomes the problem?
Where the electrons from the alkene go?
Which alkene? There's two alkenes. Which one's the most reactive?
The one on the outside?
The one on the outside, why? This one would have resonance to stabilize as well.
Least steric hindrance?
Steric hindrance could come into play a little bit. It's the stability of the carbocation intermediate that drives this. Right? So we can take our outside pi bond and react it with the hydrogen. Right? Or we could take that pi bond and react it with the H plus. Either way, right, depending on how you wanted to focus on that. And that gets us this step. We don't need to show the hydrogen connects to our structure, but we do need to specify the carbocation. Okay? This is now elementary mechanistic steps. When we talk about mechanisms, that's what you need to do. Okay? I will demonstrate a wrong approach here in just a little bit, because what that a couple people did is just jammed everything into one step. It does not happen in one step. You cannot show it as one step.
Well, it sometimes does.
It doesn't.
Sometimes
You
it does.
no, it doesn't. You have to break it apart.
SN2 does not happen simultaneously.
Because that's an elementary mechanistic step. A single elementary mechanistic step,
Oh.
yes, happens at once. If we look at what's happening behind each of these reactions, you should be able to go through and say, what was the elementary mechanistic step? So what was the elementary mechanistic step here?
Addition.
Addition is the type of reaction, that's not the mechanistic step. I know, it's hard. What's that? It's addition, you lost the pi bond, so it's not an elimination. So this becomes one of those gray things. Okay, if we're going to call it an addition, we can't call it acid-base. If you call it acid-base, the only thing that can happen is the transfer of a hydrogen. Is that the only thing that happened here? No, we've also lost the pi bond. So acid-base floats in a weird gray area for it. It's technically not the best answer because you lost the pi bond. How did the addition happen? What caused the pi bond to be lost?
The addition of HBr.
Br didn't add, just the addition of H+. Okay? To me, I would call this an acid addition. Carty goes through and calls it somewhat kind of annoyingly to me, an electrophile addition. Okay? It's not horrendously wrong, it's losing some of the chemistry because we're talking about adding an acid. Okay? And then that way we get at least a hot tip to it being kind of an acid-base reaction. Okay? We've now done our addition. Okay? Or at least our electrophile addition, our first step of it. The bromide can't come in and attack simultaneously because the bromide is stable as a leaving group. Since it's stable as a leaving group, it floats off into solution. Okay? Maybe it comes back to the same molecule. More than likely it does not. Then it just floats off into solution and we never see it again. And a different bromide comes in. What should that bromide do in this next step? Phenomenal answer. It should do absolutely nothing. Okay? Because if it did something, what's it going to do?
Immediately undo it.
It's going to react with the positive charge, which would place the bromine where the positive charge is. That's a perfectly valid mechanistic step. Is that what you were asked to do? No. So what happens instead?
Rearrangement.
Wrong R word.
Resonance. There we go. Close enough.
We have resonance. Our structure can resonate back and forth between those two systems. Okay. Now, what could our bromide do? Now, more relevant to us, it could attack that carbocation, getting us to our final product.
And it wouldn't attack the more stable carbocation because
There's an interesting question. What if it attacked the more stable carbocation? What would our product have looked like?
there'd just be a BR instead of just like right there, yeah. And then I'm on there.
What's the difference between those two products?
Thermodynamic versus kinetic.
Kinetic versus thermodynamic.
So that one's the.
That's fun. As soon as you started to say, so that one is you stopped, as in probably because you were like, I'm not sure I want to think through all of what the next word is. Okay. At least that's what would have gone through my head. I don't know if that went through your head, but that's what would have gone through mine. Okay. The one that was shown officially on the exam looks like the thermodynamic. We have the more substituted pi bond. Okay. The other one would be our kinetic, and it would be our kinetic because the intermediate
Is more stable.
had a lower activation variance, the more stable one. Okay? What should not have been shown, and I forgot that we can fix that in a second here, right, would be something along these lines. What mechanistic step is that?
Everything all at once.
That's not a mechanistic step. That was jamming everything into one thing. Okay? So to a certain respect, it's neat that you can recognize all the changes that need to happen. Okay? I get it. That's not what you're tasked to do. When you're asked to draw a mechanism, you have to draw each of those individual intermediates. Okay? One of the big reasons behind why you would need to do this would be scenarios if you were being asked about kinetic or thermodynamic. Well, but I would change my answer then. Changing your process is exactly the problem. You should have the same process all the way through so that you don't have to constantly shift, because every time you shift to a different approach to solving a question, you're changing the cognitive load on your brain, and that increases the likelihood of you making mistakes. Right? So we want to be as consistent as possible as our move through to ensure that we don't make simple, silly mistakes, and we can answer all questions at all levels.
Say if it asked for the best drawing, that would be the thermodynamic. That would be the best, or
Define best.
I don't know. That's stuff you say sometimes.
Right? So what I'm talking about is best versus useful within resonance.
Okay, that's within resonance.
And typically what we talk about is useful, because the useful leads to our product. Right?
So, okay.
This particular case doesn't work because both resonance forms lead to a product.
Gotcha.
So usually when we're looking at resonance and we talk about best and useful, it's because only one leads to a product.
I think I've rethought the question of what I meant.
Oh, okay.
So say if
Fire
it
away.
asked for, because that wasn't what I meant. Say if it asked for the major product of this, would we put the kinetic or the thermodynamic, or both? We would say if it doesn't ask for both, would it in every scenario?
It wouldn't ask that.
So then
Wouldn't ask that question. So yeah, provide the mechanism. Okay. What I could say is, here's the reaction. Draw me an energy diagram showing me the difference between kinetic and thermodynamic. Draw me a mechanism for each of them and point out why they're different. How this changes which product you would get out of it. Okay? And the big issue kind of with this one, we really just have, what, 2 steps? So we have one intermediate. See if I can pull this off.
You say that every time.
The kinetic and thermodynamic are hard for me to line up the end result with. Is this crossover at the end? They're still technically going through the same intermediate, but that resonance form drops that activation barrier. Okay? The overall difference in energy between these, reactant to product, is so similar that we're not seeing a huge differential between kinetic versus thermodynamic. Okay? We could try to push one versus the other by changing the temperature. So we could drop in and say, this is run cold. Well, if it's run cold, what product should I get?
The kinetic.
I should get the
I
kinetic.
keep trying to say kinematic. I don't know why.
Unfortunately, I don't know why either. If we said hot, what should we expect?
The thermodynamic.
The thermodynamic. Okay? Very subtle differences allow for this. What we're going to find in this new unit is that our energy diagrams are going to switch up. Instead of, and we'll just do one hump here, instead of being nice, simple, almost equilibrium-based reactions, we're going to start to see some pretty big extremes in that differential. Okay? Looping back to the very beginning of this class, we can talk about the acid-base reaction, acid plus base, with hydride. If I use the hydride, what does it produce? It produces hydrogen gas. Right? The first product I get, regardless, is always going to be the kinetic. What's the problem with hydrogen gas?
Very unstable.
It's gone then.
It's a gas. It bubbles out of the reaction. And if it's out of the reaction, do I have a reactant to reverse? No. Okay? So that reaction becomes irreversible. It's impossible for me to get to the thermodynamic. Okay? I can heat it up as much as I want. And all that's going to happen is it's going to explode. Okay? Because I heat it up and the hydrogen gas ignites. Okay? That's not a good process. Okay? So heating it isn't going to help me. The other thing that you'll note is that we get a huge activation barrier for the reverse reaction, also making it very difficult to reverse. Why? Hydrogen gas is stable, H minus ain't. Okay? So we get a huge favoring for our products. Okay? And so the term that's going to come up, which came up in the kinetic and thermodynamic video, was this reversible and irreversible. Those terms are very, very challenging, and they're really only referring to the kinetic reaction. And when we talk about reversible, we're saying the kinetic product was reversible. When we say it's irreversible, the kinetic product is irreversible, which is why I only get that product. The thermodynamic product will always be irreversible. That's why it's the thermodynamic product. It's the lowest energy. Okay. And if you really want to push it, everything is technically reversible, but okay. Talk too long, I'm stopping.